Hey, welcome to next instalment of one of our screencasts here. We're going to target today about horizontal circular motion, section 3.2. Before we do that, we'll just recap the important formulas that we had covered, which will apply to all of our circular motion, doesn't matter what kind it is. The most important one really was, and I'll highlight it there, there you go. Our force is equal to mv squared on r. Now, when we focus on that force there, what we're talking about, of course, is the centripetal force. All right, so whenever we see that, it's the centripetal force. And the last lesson we said was that if something's going to move in a circle, your centripetal force is your net force. Overall, the sum of the forces on the object have to be centripetal, in other words, towards the center of the circle. Okay, and whatever applies it depends upon the situation. Then if we pick apart that formula, don't forget, we look at the proportionalities. First of all, the first one, that the centripetal force is proportional to the mass of the thing that you're trying to make go in a circle. So the bigger the thing, the more force you need. Kind of logical, makes sense. Okay. Similarly, your centripetal force here is proportional to your square of your velocity. And that's a significant result there in terms of, if you want to go faster, if you want to double your velocity, your tangential velocity, you need to have 4 times your centripetal force. So things like racetracks, anything spinning, or obviously has implications there. Lastly, for athletes, this is an implication. We talked briefly last lesson about how if you want to go in a really tight circle, for example, in sports where you have to change direction quickly, basketball, AFL, for example, your force is inversely proportional to your radius. So turning a really tight corner takes more force than turning a corner with a large radius. Okay. Now, so let's move on. Like it says, we'll consider the 3 scenarios of circular motion. We're going to do horizontally today, and then we'll look at vertically, straight up and down, and then at an angle, things like bank tracks and velodromes and stuff like that. Okay. So first one, horizontal circular motion. What it's saying here is this, is that in the vertical direction, okay, your net force is 0. Nothing's accelerating up or down. It's all balanced in the vertical direction. But of course, your net force in the horizontal direction is supplying your centripetal force. So there's no acceleration vertically. Everything's happening in that horizontal plane. Okay. A good example, of course, would be if we look at task 12 here. A stone is tied to the end of a string, swung in a horizontal circle. How will the rock move if the string breaks? We'll do, if we make them part A and B, and then we'll do C. Okay. Pause now. Have a think. You should have a fair idea for A and B, and then we'll come back and have a chat about, see how you went with A and B. Okay, so if we have a look over on the right hand side here, I've got a diagram of a pretty typical horizontal circular motion setup. In this example, it's obviously your centripetal force is actually going to be supplied by the tension in the string, which is equal to the weight, mass times gravity, of whatever that weight there is. So that string kind of goes up and then through and keeps it going in circular motion. Okay, let's have a look at number 1. It's saying what will happen if the stone breaks. Key words in that answer would be tangential. So if you said something like it flies off tangentially in a straight line, and then it will of course become a projectile. Secondly, why can we ignore the effects of gravity in this circular motion question. Okay, we go back to our understanding of components, and we know that gravity is acting straight down. What it means is that there is no component of gravity acting in the direction of motion at all times. It's perpendicular to our net force or our centripetal force, and that's all in the horizontal direction, whereas of course mg is vertical. Okay, don't get it confused with this mg here. That's the one that's actually providing the tension in the string. Okay, I'm going to rub that out and have a think about part C here now. Okay, is it possible for the string to move in a perfectly horizontal plane? Okay, no. We'll see why. Okay, what happens of course is if we have our mg back there again, there's no weight force in the vertical direction to counteract that. At any time, there's going to have to be at least a little bit. I've over-exaggerated it here, but at least a little bit of an angle in there so that the object is going to be slightly below the horizontal. What that means then is that if I pop the tension back in, so there's our tension. No, now actually, there's the tension in the string. You're going to need at least some component of tension acting upwards to counteract the weight force of whatever that object is. Okay, so realistically, you're going to have a tiny little bit of an angle in there. You can get it really close, but the closer that angle gets to zero, then you probably have some idea that the tension in the string, as that approaches zero, the tension actually tends towards infinity, which is not realistic. We'll look more at this situation a little bit later when we look at conical pendula. Okay. All right, let's look at example 1. This should be fairly straightforward, okay? Take a pause, R, T, F, Q, and then we'll come back. Okay, so we've read the question, and the question saying is what speed will it leave the slingshot? So we go to our formulas. V is 2 pi r on t, which is exactly the same as, distance over time. Okay, it's saying it's got 2 revolutions per second, so our period is half a second, or what we could say is the frequency is 2 hertz. So 2 pi, our radius is in meters, 1.2 meters, and instead of dividing by half, all I'll do is times by 2. So 4 times pi times 1.2. It's going at 15.08 meters per second. We check what's speed, so we don't need a direction, so we're all good. Secondly, part B, the tension in the slingshot's string. What that's essentially asking is, what is the centripetal force? Okay, so we recognize that the tension supplies the centripetal force, and if we look up to the top of this page, it's just mv squared on r. We know m is, the radius is 1.2 meters again. We've worked out our v, 15.08. Don't forget to square it. And, oops, sorry, go back a little bit. Our radius was 1.2, our mass 2.3, and it really is that simple. 435.86 newtons. But what we need to remember is that's a force, so it's a vector. So we need to give direction T, C, O, C. Okay. Rewind a slight bit. I just want to go back to part A here, and I meant to have a little little go off on a little slight tangent, if you pardon the pun. Obviously, if the string breaks, it'll go off in a tangent, and we've got to mention that famous piece of sporting history where it was just over 20 years ago now, Salt Lake City, as you can see, 2002. Okay, famous piece of history with guy Stephen Bradbury, short track speed skating, grand final gold medal match, was coming last. What's happened, of course, is to keep going in a circle, the skates dig in quite viciously on the circle, on the track on the ice. What that does is provide a reaction force, and I'll do that in red. That provides a reaction force, and there's that inwards component of the reaction force. I'll call it R cos theta, if there's theta. So they provide a reaction force for you to be able to go in a circular motion. As soon as that reaction force becomes zero, as evidenced by the three other guys there in the photos, as you can see, okay, this guy was leading at the time, hence he was further around the circle and went off on a tangent, slightly forward of the other three. So you can see how they've just gone off on a tangent and behaved, so obeyed Newton's first law of motion, continued until until a force makes them stop. And if you really want to pause, you can watch the whole race there. I've thrown that in there just for good measure. Okay, so if you want pause, have a look at Stephen Bradbury, and we'll meet again on page 30. Okay, so next page here, guys, we've got an example where it says the Earth maintains an approximately circular path. So we, at any point, even though it's not perfectly circular, we can make a pretty good approximation at any point. We've got the radius of orbit, we've got the period, but we don't have the velocity. Okay, and notice that the period's in terms of days. We've got the mass of the Earth, and what's the average gravitational force, i.e. what's the centripetal force, because it's gravity that's supplying the centripetal force. Okay. First thing we'll do is, because our period is in days, we'll change that to seconds or SI units. Now there's 86,400 seconds in a day. Handy little shortcut. So that gives us 3.156 by 10 to the 7 seconds is how many seconds there are in a year. Okay, so our centripetal force, or the force of gravity, is mv squared on r, but we don't know the velocity. So what we'll do is substitute 2 pi r on t for velocity, and that becomes 4 pi squared r on t squared, and don't forget to multiply it by the mass, because there's m, there's v squared on r. Okay, so now it's just crunching numbers. 4 pi squared, our radius was 1.49 by 10 to the 8th. Okay, and our mass of the Earth, 5.98 by 10 to the 24 kilos, sorry. Okay, form and data sheet, check it if you're not sure. Our period, 3.156 by 10 to the 7 seconds, don't forget to square it, and there's our answer there. I'll cheat. There's our answer, and don't forget, because it's a force, we need a direction. If we want to be particular, towards the center of the sun, because the center of mass is of the sun is what that force will be directed towards. Okay, so some fairly simple applications there of horizontal circular motion. Okay, let's look at another example here, and a slightly more difficult example is when we look at conical pendula or pendulums. Okay, textbook, page 69. what we've got here, as it says, you've got a string is sort of often fixed at a certain point. You've got a length L, you might know the radius, and if you know the hypotenuse or the height or the radius, we get a nice right angled triangle here. So often you're not actually given what the theta is. Okay, I just want to give you a bit of an introduction to this, and we'll explore them a little bit further when we do motion at an angle. Okay, so like I said, you'll often have a right angled triangle, and what we do know is we've got our forces. We've got the weight force, and you can see that force there in green. I'll make it bigger and make it red. There you go. There's the tension in the string. They're the only two forces that are applying to that object there, the ball. A way I like to approach this is we now look at the tension, and the tension has two jobs, the tension in the string. The vertical component, and I'll call it T vertical, is equal and opposite to the weight force of the object that's spinning in the circle. Because remember we said that because it's perfectly horizontal circular motion, there's no net force vertically. So if we go over here, we say our net force in the vertical direction is 0. In other words, that vertical component of the tension, which is going to be T, if that's theta, we're going to have T cos theta, is equal and opposite to the weight force of the thing that you're spinning in a circle. Okay. So there's vertically. The second job that the tension has to do here is the horizontal component. You guessed it. That, I'll call it TH, or we could of course go X and Y, as we know. That is what supplies the centripetal force. That's our net force in the horizontal direction. Okay, so our centripetal force is going to be, oops, not mg, T, not T cos theta, but T sine theta. That's what supplies your centripetal. Oh, that is our net force in the horizontal direction. Okay, and when we look at our net force, it doesn't take too much to see that in terms of the weight, your net force is mg tan theta. I'm not going to do it here. Have a look, have a pause, have a look at it if you want to, if you wish. Okay, so it's pretty well over to you now for a wee bit. In our textbook, look at the worked example, chapter 2, section 4, number 3, and then right after that is the try yourself and do that here. Okay, so that's to do that's task 13. Next up, straight off, is continue after you've done that and get on with our independent work. Again, page 71 to 72. It's the end of section 2.4, which is all about horizontal circular motion. Okay. Now, it would be remiss of me if I didn't have a little joke at the end. Instead of a joke, because we've got it on the screen here, and I'm hoping that's still going to work. Because it got that on the screen here, what we're going to do is, there you go, well, that's going to be about right. We've got to show a little cat video for sure, instead of a joke. Horizontal, approximating horizontal motion, and then becomes a projectile and obeys Newton's first law. Thank you.
Turn off
Gotta love them. Cheers.